All right. So in this video, we will be proving f RKF equals RK inverse, right? Where we are talking about the dihedral group of n-gons, and F represents a flip and R is a rotation. All right. So now before we dive into the proof of this thing, I need to explain a little about the dihedral group. Okay. So I'll do that by an example of D4, or we write it as D8, symmetries of a square, right? Now, see, a flip and a rotation. Let's try and understand what they do. So this is, say, my square, right? Now observe carefully the order of the numbers. Okay, they are running in the anti-clockwise direction, right? Okay, so now think of it. Whenever we rotate this, will we ever be able to change this orientation of numbers from anti-clockwise to clockwise? No. Okay, we can never do that, right? And now look at this. What I'll do is I will flip it across, say, this diagonal. Okay, so what it will do is that it will keep the diagonal entries fixed, and it would flip 2 and 4, the position of 2 and 4. This is what a flip will do. Okay, now observe carefully what happened to the orientation of our numbers. Now they are running in the clockwise direction. Okay, this is how I understand this concept, that a rotation, no matter how many rotations we do, we will still end up with the same orientation of numbers, that is anti-clockwise. I take it anti-clockwise, you can take it clockwise first, and then whatever, doesn't matter. Okay, so, and what a flip does is that it reverses the order of these numbers, right? It reverses the order. Now just imagine what will happen if I flip it again. Of course, the same. Okay, okay, not the same. Let me now flip it across, say this diagonal. Okay, so what will happen is now 4 and 2 will remain fixed, and 1 and 3 will change positions. Look at the order now. 1, 2, it is again running anti-clockwise. So this is a rotation actually. Okay, now if this was, say, this was my identity, then this is my R. By how much degrees did I rotate it? 90 and 180. Yeah, this is R 180. So I rotated it 180 degrees. But I did not actually rotate it. I flipped it twice across different diagonals, different axes. Okay, so make this clear. Make this concept clear in your mind, that two flips will always result in a rotation. Okay, no matter what our polygon is, two simultaneous flips will always result in a rotation. And if those flips are the same, like in this case, if we flipped it across this diagonal and then we again flipped it across this same diagonal, then we would have reached back to E. Okay, so what this means is that, yeah, we know this very well, that order of a flip order of a flip is 2. That means f square gives us identity, right? And what this means is that F operated on F gives us identity. And what this means is that F is the inverse of itself. Okay. Now, one more thing before we dive into the proof. Yeah. Let's take a look at this. RF. And why I look at this? Let me write again what we have to prove. We have to prove that F R to the power K F equals RK inverse. Right? This is same as RK inverse. Okay. So why I wrote RF, yeah, that will be clear in a moment. Now just try to figure out, pause the video and try to figure out what RF would be. Now, and this is operated according to the rules of function composition. So we operate F first and then R. That means we will flip first and then rotate. Now remember, a rotation keeps the order of the elements, no, not elements, keeps this order 1, 2, 3, 4. A rotation will not change this order, but a flip will. Now, right? Now we flipped it, so we changed the order and then we rotated. So the order is still changed. So what this implies for us is that this RF is ultimately a flip. Okay? Now since it is a flip, and we know, look, the flip, square of a flip is identity. That means a flip is its own inverse. So from here, I can conclude that RF square will be identity. And now, finally, we can begin the proof of this. And how I'll prove this is by using the principle of mathematical induction. All right. So, yeah. So for I'll take k equal to 1 and I'll prove that this is true for 1. And how I'll prove? Let's see. So what I'll do is, yeah, I'll start with this. Okay. Now RF square is E. That means RF times RF is E, or RF operated on RF is E, right? Now what I should do is, yeah, I left multiply by R inverse. Okay. R inverse. And why did I do so? See, if this K is 1, I would need FRF, right? And if somehow I'm able to eliminate this R, then I'll be left with FRF. That is why I went for this R and I multiplied it by R inverse. Okay. So in next step, this will become identity, and identity into anything is again the same thing, right? So I'll be left with FRF, and on our right hand side, I'll be left with R inverse. So I proved this for k equal to 1. And now I'll prove it for, no, now I'll assume it to be true for k equal to n, and then I'll prove it to be true for k equal to n plus 1. Okay, and if n is confusing, let's take this p. Okay, and if this is confusing, okay, yeah, let me explain it. Usually how we do induction is that we have to prove for n, we prove for 1, we assume it to be true for k, then we prove it to be true for k plus 1, and then we ultimately say that is also true for n. So in this particular case, I already have k here by chance. So I proved it for 1, right? Now I'll prove it for, now I will assume it to be true for p, and then I will prove it to be true for p plus 1, right? So now I have f r f equal to r inverse. I have proved this. Now I will assume that it is true for f r p f equal to r inverse p, right? And I will prove it to be true for p plus 1. Okay, let's get to this. Now p plus 1, how do I reach here? Okay, say, yeah, look carefully. If I remove this p, this f somehow, and I get here another r, right? Let's try this. F R. Okay, let me change the color. So what I'll do is F R P F F inverse. I will multiply it F inverse, and I'll get F inverse here. So I'll get F R P equals R inverse P F inverse. And if you remember, F inverse is F itself. And by chance, we have proved yet another thing, which is written in the books as r to the power n s equals s r to the power negative n. Okay, this is in a way the proof of that. Yeah. Okay. Now, okay, let's get back to our proof. Yeah. Now, I don't think I got anything from this. Okay, let's take the left hand side. I have f r p plus 1 f. Okay, I have taken the left hand side of what I have to prove. So I will break down r into r to the power p and r and f. Yeah, right. Okay. And from here, look, what I have to prove is this is equal to r inverse of p plus 1. I have to prove this equal to this. Okay. So, yeah, let's come back to this. Now, I hope this is clear. I broke down this into r to the power p times r. Okay. So the next step is that I should replace this with this, right? I substitute. So I'll get R inverse P F R F. Okay. Yep. And when I proved it for k equal to 1, I proved that F R F is equal to R inverse. So now what I'll do is I'll substitute this into this, the value of F R F. And what I get is R inverse P and F R F is R inverse. So this gives me R negative P plus 1. Right? So ultimately, I prove that F R to the power P plus 1 F is equal to R inverse of P plus 1. So, by the principle of mathematical induction, I can say that F R K F equals R K inverse, right? And sorry, this pen seems a little lighter. But yeah, this is the proof. It is a little tricky, so if you somehow reach till the end and are still unsure about it, watch it again. And if still not clear, then just hit me in the comment section and I'll clear any doubts.